Thanks everybody for coming. Whenever I have a talk that has specification in the title, I am always amazed when there are 5 or 35 or 500 people, because it's 5, 35, or 500 people more than I expected would have come, just based on the title alone. So all right, thank you very much. So you guys are, just to be sure you're in the right destination, you are on the flight marked Index 3D Scene Layer Specification. And with me today, I'm very lucky to have Isaac Zworsky, the Vice President of Rikon. You've certainly probably heard about them, or at least seen their data presented up on the main stage. Adrien Mériot, the French guy, pronounced their name quite awesomely this morning up in the Dev Summit plenary. And they've been a fantastic partner to demo 3D with. And then Tamrat is with me as well. Tamrat is one of our critical lead software developers. He is my go-to person for any troubles that I'm ever having around these scene layers. So he's the man. And then you've got me. I'm the lead product manager for 3D at Esri. I refer to myself as an irritant to all the other product managers in trying to get them to make their products more 3D. And you can see this year, if you walk around the show floor, that we've had some significant success because 3D is now literally just about everywhere. So I'm going to do just a really quick intro, give you guys some context. Isaac is here because he's actually going to show you how their data works with this specification in our products. And then Tam is going to do the deep dive that you guys are really here for. All right, so 3D at Esri. I've been telling people that there's a very subtle message in this slide. It's not just that Geospatial 3D is already around us, it's that there is a veritable tidal wave of 3D content, applications, use cases that are coming out of the woodwork that we as an industry need to start to service. And these guys are a perfect example. How big is your globe of the world going to be?
About 230 terabytes.
Right. So these guys are intent on building a mesh of the globe, and 230 to 250 terabytes in size. And we know one big government customer that is targeting absolutely having access to that. And it would be fantastic if Esri could have access to something like that to serve it out as well for you guys to use and experiment with. So that's just one tiny example of the massive amount of data that's available in the 3D world. And what we're here to talk to you about today is a specification for serving it. The types of data that we are attempting to cover with this specification include things like 3D city models, everything from untextured, what I call the gray or white box buildings that I actually kind of despise, to the really pretty textured models, to thematically textured models, and procedural models, and city GML stuff, and all kinds of other things in between. Massive tins. I use the word tin because that's what these guys use on their website. We have a format layer profile for these called integrated mesh. We'll talk about that a little bit more. And they can be huge. A single file, the largest one that I have on my machine is 120 gigabytes. So they're big. And 3D has helped us introduce GIS to the real world of big data, for sure. And then point clouds is another example. Massive amounts of point clouds. The point cloud layer you saw on stage this morning, I don't know if you caught it. I suspect a lot of people heard it, but then it passed right through. It was 60 billion points. That was the number that he used. The Barnegat Bay example that you can access up in ArcGIS Online and experiment with is 1 billion points. And then we just rolled these out recently, and we'll be doing tons more with them down the road. Our goal with this scene layer specification that Tam is going to talk about is to enable us to distribute these really massive data sets throughout the really big platform that is ArcGIS. So it's not just to drive 3D into a single extension or a single product, but actually to allow you to consume and deliver it to GIS experiences across extremely large enterprises or extremely large workflows. 3D is deeply embedded with the concept of open for us here at Esri. Jack has this vision for open and Esri, and it includes open source and open data and open standards. And with 3D, we are embracing a variety of existing open standards, including things like KML and WMTS, WMS. We've released a patented compression format for raster data that is partly how we serve out our 200 and I think it's 40 terabytes of elevation service that we have, and you have access not only to the elevation service but also to the format and the compression technology. And then index 3D scene layers are this scalable scene cache that we've created for enabling you to serve out the types of layers that I just mentioned. You're going to hear a lot more about I3S in the future. We've submitted to OGC for consideration as a community standard. It's already shared under Creative Commons licensing, has been since 2014, early 2015, I think, yeah. And we see it as an essential component of distributing 3D content throughout ArcGIS in the future. And it's also meant to be able to enable us and partners to distribute content to non-ArcGIS clients as well. You don't have to be using Esri technology to use it. In fact, these guys make it without any Esri technology. So then two of the concepts that we've introduced with 3D are web scenes and scene layers. In my Chris speak, web scenes are basically containers for layers, environment settings, bookmarks, and other things that are transportable across the platform. So you can use them in Pro, online, portal, the scene viewer in the browser, and then later this year you'll be able to use them with the runtime SDKs. And then scene layers themselves are these scalable caches of graphics that you could think of as feature services, but just with an entirely different format and structure for serving out really massive amounts of content. And then we've got third parties that are starting to adopt I3S. These guys are Star partner who's adopted it. Pix4D has adopted it. Bentley started creating I3S from context capture without really even consulting us, and that's fantastic. They needed to do it because they don't have any place to put their big context capture data sets. Safe Software is in prototype with an export I3S workflow, and there are several, actually many others that we've talked to. We expect more and more to come online. And then just the last comment for me is the types of workflows that our customers who use 3D live in are the same types of workflows that our customers who used 2D yesterday lived in. It's just that customers are looking at new technologies, new capabilities, cheaper access to stuff that existed for a long time, more ubiquitous access to stuff like LiDAR that existed for a long time, and now they want to use it. And so our job is to help you guys figure out how to use that for your customers, for our combined customers. So, all right. So with that, I'm going to switch over and allow Isaac to start demoing. Go ahead.
All right. So thank you for the intro earlier, by the way. So just to kind of set the scene and the context for how we got to be here. Quick background on Vricon as a company. So we're a little bit of a weird company. We're the product of a joint venture between Digital Globe and Saab. And our mission in life as a company is very much to just go out and build the highest resolution, most accurate 3D map of the face of the planet, and then actually host it live as a web service. So what we're talking about here today very much comes into play when we start talking about the accessibility and the distribution and the exploitation of the kinds of data that we build at a very massive scale. So I'm going to jump over here real quick, and I'm going to pull up ArcGIS Earth as a place to start. So when I say massive scale, we have a big data center out in Virginia. We pull in many tens of millions of square kilometers of satellite imagery each week. And we use completely automated multi-view stereo algorithms in order to generate hundreds of thousands, if not millions of square kilometers of 50 centimeter resolution textured 3D data each month. So that's a lot of data in general. So for any of you who have been involved in the 3D world for some period of time, I've been in it for quite a long time, you all probably recognize that one of the biggest challenges and hurdles with 3D content in the community was the fact that the data traditionally has been very heavy. So either raster products or point cloud products have been very heavy, and the tools that you need to actually be able to exploit them have been very cumbersome, have required heavy-duty hardware, and have generally been very expensive and kind of niche focused. So as we're coming into this space and generating massive amounts of content, one of the big challenges that we face is just being able to get that content to the broader community and get it to them in such a way that they are able to actually do something meaningful with it. As Chris kind of alluded to with his tidal wave graphic, the recognition from the industry and the community is that 3D is a core component of everything that we're doing today in the GIS space. You heard it on, if you were here for the Partner Summit, you heard it on stage from Chris Capelli saying that Esri's customers are telling him that 3D GIS is the only GIS, and that's very much the case.
I'm responsible for that line, by the way.
That's right.
It's my fault that he's having to say that. So.
And the more feedback from users, customers, partners, and developers to Chris and then to the rest of the team, the better, because that just helps my cause for trying to get Chris more resources to move this faster. But that's a shameless plug on my side. So to jump in real quick, I'm actually going to remove this and just go straight. So we're in ArcGIS Earth. So one of the really powerful things about the integrated mesh standard, or the I3S standard, from our perspective, is that it is natively supporting a tiled textured mesh data format in and across the ArcGIS platform. So one of the really powerful parts about that is that that we, as a partner of Esri's, can independently implement the I3S spec as an export option on our own side in our own software, and we can export our data sets directly from our own data center as scene package layers that we can distribute to our customers, and customers can either push them up to their portals, push them up to ArcGIS Online, or utilize them locally, and in any one of those scenarios, they can be used in a lot of different ways in the platform. So I'm going to start by just jumping in here and adding, we're logged into actually Chris's ArcGIS Online account, which has been connected to an organization that we have in ArcGIS Online. So we have for a while now been pushing up data sets for sample, for demo purposes and testing, and trying to push on Tam and the team to see how big we can go and all sorts of fun stuff like that. So this is my organization. This is the Recon organization inside of ArcGIS Online, and I'm just going to pull in a couple of kind of data sets that we have posted there, just to kind of show version 1 of what this type of data can actually look like and what you actually get out of it. So what you're looking at here is 3 geocells, so full 1 degree cells, or 1 degree by 1 degree, roughly 10,000 square kilometers, depending on what latitude you're at, of 50 centimeter resolution, fully textured 3D content with an absolute accuracy of 3 meters, SE90, so in all 3 dimensions. And I just connected to these as scene layers inside of ArcGIS Earth. And as you can see, as I come in here, the data is going to load in that pyramidally tiled way that it does. I think we're working off of the Wi-Fi connection here.
It's wired.
Potentially. Oh, it's wired.
It's been really slow today. I don't know. Online must be getting slow or something. But.
Yeah, there you go. So, but what you're looking at is the live streaming of this content in real time. So wired or wireless, slow connection, you're getting a sense for the kind of performance that you can get with the 3D content in this indexed scene layer format. And again, for any of you who are familiar with having to do analysis or exploitation in 3D content, so point clouds or raster types of 3D content, being able to, so I just zoomed into a little place down here just south of the border in Tijuana. And now I can kind of jump back out and say, oh, I actually want to jump up here to, I don't know, LA or somewhere fun.
Yeah, and so this is about 120 gigabytes of service, of package data that was then uploaded and converted into services automatically and online. So, so it's a significant amount of data that you're able to dive in on and investigate.
Yep, very much so. And the 120 gigabyte number is kind of a good lead-in, because so what you're looking at here is me just connecting to services that are hosted inside of ArcGIS Online or in the enterprise environment. But one of the cool things that Earth does is that you can also jump over here, and here Chris has a selection of local versions of some of these data sets that we had, to include this one, which is I think the largest one that we've delivered to them to date. It's 120 gigabytes of, so this is a single geocell that's 120 gigabytes as a single scene layer package. And so inside of ArcGIS Earth today, we can actually drag and drop that data set directly into the application, and it's going to take a few seconds to load, but it's going to take a few seconds to load. So the concept of being able to actually load 120 gigabytes worth of high-res 3D content in that fast, I've been cutting it down every one of these demos that I do. I started with 45 seconds, then I went to 15, but I swear that was about 8, so we're getting better. So this is another 1 degree cell. This is content actually up over northern California in the Yosemite National Park. So you saw some of this content on stage this morning, but this is that full data set. Again, the ability to run and load content that fast is a huge deal, right? So I like to use this little anecdote to kind of illustrate why that's kind of powerful and important. So we just had a big government customer who made a purchase of a bunch of data, and the delivery that we made to them actually ended up being roughly 30 terabytes worth of content. And it was in response to a very urgent need from some of the people that were there. So 30 terabytes worth of content you hand to a systems administrator who manages the geodatabases that they have, and they tell you, okay, come back in 2 weeks and you might be able to get some of it. And then indexing time on top of that as well. Whereas all of that content, the actual high-res 3D content of that was just a fraction of that 30 terabytes, and that could have been published as a scene layer and actually shared like that to a point where the people with the urgent need could have accessed it on the same day, right? And that's a huge dynamic kind of like mind shift in the industry, because it means that people for whom 3D was either too hard, too complicated, too expensive, or too heavy to actually be able to use for the types of analysis that they do on a daily basis, now it's just easy, right? So ArcGIS Earth is kind of a great example of easy. It's free application, anybody can download it. You can come in here and you can drag and drop and play, and you can drop points and actually do measurements inside of the scene like this. But in the wonderful way that Esri as a platform enables you to do a lot of different things, those same services that you were seeing inside of ArcGIS Earth, we can come over here and pull up inside of a web scene, right? So this is actually and I always have to remember the rotate commands between Pro and everything else really annoy me, but.
Very religious.
Yeah. So this is a web scene that Chris threw together, and you'll recognize several of these geocells that we were just looking at inside of ArcGIS Earth. Here they're published as a web scene. The exact same content, now rendering in a WebGL app.
And this is over 400 gigs in the same, that can be accessed in this scene.
We'll come back down to Yosemite just to give some kind of appreciation for similarity of what you're looking at. But again, it's the exact same data, exact same content that you're looking at, exact same service, just connected into a web scene this time. I have tested I have tested these on mobile applications. They kind of work sometimes. Okay. Sometimes. Chris promises me he's working on actual mobile applications sometime in the near future. But
I'm not, but somebody is. The online's been a little.
Yeah, so we'll blame this on online, but you're getting the picture here. The exact same content that we were looking at before is now coming in into your WebGL app, which is a very cool kind of scenario. And again, from a usability standpoint, this just opens the door even further to a much broader spectrum of people who can derive great value from having access to data like this, but likely would have never been on the short list for having a full license of ArcGIS Desktop or name your other point cloud exploitation tool, right? So taking this one step further from this kind of pure textured 3D content, one of the things that we do as a company in order to be able to support a lot of the legacy workflows that do exist in the community is that we do direct exports from this textured 3D scene mesh space into traditional formats as well. So from the 50 centimeter resolution, fully textured 3D models, we can also do a direct export of a 50 centimeter digital surface model as a raster, true ortho, so a native rendering of all the texture pixels in the scene, or even cut a whole bunch of holes in the mesh and spit it out as a point cloud if you happen to like that. So one of the cool things that Chris did just a couple of weeks ago when we were at a meeting for OGC, technical exchange meeting for OGC, talking about these types of formats, is he took samples that we provided in all the different formats and flavors that we traditionally expect people to use in a bunch of different tools and different tool sets and workflows. And he took all of them and actually was able to generate scene layers from all of the different types of products over the same regions. I can never remember which ones of these are the most fun to look at right off the bat. Oh, that's a good point. So here we can start with DC close-up. So this is the textured 3D seed mesh that we were just looking at over in Yosemite. So same content. Here just loading in over from a model that we generated over DC. This is the point cloud layer. Again, it's going to stream in here as we actually watch it load. But this is the point cloud that we extracted from that textured 3D mesh. Exact same content, perfectly correlated, exact same accuracy metrics through and through, and actually the same RGB values are encoded in the pixels. Here, Chris has done a false color height texture. But the exact same content now hosted as well as a scene layer. Same content, which is very cool. Here we can jump to the other side of the world and take a look at a similar example.
Some people have asked me why customers want the same data as mesh and DSM and point cloud. And the reality is a lot of these data types, especially the mesh, is brand new. You can't use it everywhere yet. But point cloud has been around for a long time. DTM has been around for a long time. You can do analysis against those that you can't yet do against some of the big meshes. So eventually that will happen, but for today, this is why the customers need these different data types.
Yeah, and that's a great point. So we, again, I'm going to put the shameless plug in for those of us in the group to keep pushing on these guys. So we we're a little unique in the way that we approach the geospatial world, because a lot of our developers come out of the modeling and sim world, where textured meshes are where you start from. So we do everything in textured mesh space. All of our building, all of our QA/QC, everything that we do internal to our company is done in textured mesh space. And we actually even have done a lot of work in implementing analytics, things like line of sight analyses and flood analysis and all sorts of other things in textured mesh space. And we've had a lot of success with it because there's a ton of functionality that's built into OpenGL and other libraries like that coming out of the video game industry, coming out of the mod sim space, where you can actually do a lot of those analyses on textured mesh directly, but at kind of performance levels that you could never hope to achieve in traditional raster space or in point cloud space. So I keep pushing on these guys to get to the point where they start actually implementing some of those things inside of the Arc platform. So ideas that you guys have, keep pushing on them as well. But Chris is absolutely right that currently, and this is exactly why we export in a bunch of different formats and flavors, we want to be able to support all the different types of analytic tool sets that do exist with the data types that work best. And it's cool that we can push them all into the same layer spec. So I think with that, yeah.
Do me one favor, click on the last top. So just so that you guys can be convinced that it's not just FrightCon data that can be shown in this. What we actually have in this scene is about 5 different Revit building models that have been converted into 3D object scene layers. And then these came from the University of Kentucky. They've been kind of a research partner with us. And we're working on extending the spec into even more data types. It's definitely not something that's arrived at a final destination yet. This is a living thing that will continue to progress. And as you guys run into new data types and formats that you'd like us to cover, please let us know. BIM is a major focus for us for the next year or two, I'm guessing. So, all right, with that, definitely, Town. Sure. Thank you very much, Isaac.
Cool. So this is great, Isaac. Thanks again, and Chris. It made my job much easier. I don't have to do demos. So you asked about spec, and we'll talk about the spec a little bit here. So yeah, I3S or Index 3D Scene Layers is supported by a variety of software products, including Recon, Bentley, Pix4D, which we actually use internally in Drone to Map application to generate integrated mesh type of content similar to Verizon showed here. And then also SAP software, as Chris mentioned earlier, are also in development supporting I3S. But now I wanted to talk about where within the ArcGIS platform I3S layer really kind of stands. And there's a pervasive support for I3S within the ArcGIS platform. And let's just go a quick rundown of the suite of products that we have that supports I3S, both from publishing or content generation point of view and also from consumption. So the first one that comes into mind is ArcGIS Enterprise. Of course, this consists of ArcGIS Server, ArcGIS Portal, backed by ArcGIS Data Store and a web adapter that allows you to publish content directly to your own enterprise organization. Next up is ArcGIS Online. You can publish directly, as they have shown throughout the examples, directly to ArcGIS Online, a scene layer package that could be also consumed within a desktop application and also as a web service through the REST API. Drone to Map is another, Drone to Map for ArcGIS is another product that actually supports outputting integrated mesh layer types, integrated I3S layer types, and Drone to Map content could also be used again in a variety of products that we have. This year, Esri City Engine 2016.1 added the ability to output I3S content. SLPKs are now you are now able to generate an SLPK out of Esri City Engine. So that's also a great addition to the suite of products that we have. And then lastly, but not least, of course, ArcGIS Pro is the premier desktop application that we have that serves as a desktop application that can generate scene layer package directly, and also is used to push content or to push content to ArcGIS Online and your ArcGIS Enterprise. So ArcGIS Pro actually has this dual nature in being able to generate the content directly in there, or just being able to publish content that gets eventually generated in the backend in the ArcGIS server. As far as consuming it, obviously the ArcGIS Online web scene can consume I3S layers. Your portal can directly, or ArcGIS Enterprise can directly consume I3S layers. And brand new now at ArcGIS API for JavaScript is the ability to be able to actually consume scene layers within the JavaScript SDK is also great. We've already seen people actually building cool apps around that, and we envision that this is going to grow even bigger. So that forms the web tier that we have as far as consuming I3S content is concerned. From desktop, I don't need to delve into it that much. Again, ArcGIS Pro is a client that can consume I3S layers, both direct access of SLPK, as was shown in Earth, and access of scene service layers via the REST API is possible in ArcGIS Pro and also in ArcGIS Earth. And then lastly, one thing that we have released was ArcGIS Runtime version 100 release is the ability to consume scene service layers directly within the ArcGIS Runtime application. So this is also an exciting frontier for us to be able to consume really I3S services and content in mobile, desktop, and web applications. So with that, let's go talk about a little bit about the I3S format and its structure. So index 3D scene layers, what is it? Supports storage and transmission of very large data consisting of millions and millions of discrete 3D objects with attributes, as well as we have seen integrated mesh surfaces that may cover millions of square miles. It was designed from the ground up to be both cloud and web and also mobile friendly. And that the I3S tenet is that it is all based on JSON, modern web standards, and REST APIs for being able to access this content. I3S Index 3D Scene Layer supports geospatial content as well as the required coordinate systems. So you can generate content in a projected coordinate system or in a geographic coordinate system to fit your viewing and analysis environment. Also including the height model or the vertical coordinate systems that are required mostly to fuse different data types, along with a rich set of layers are supported within I3S. So an I3S data set, we can refer to it as a scene layer, and it is a container for arbitrarily large amounts of heterogeneously distributed 3D geographic data. Chris already mentioned this. We already submitted in OGC community standard, so we're going through that process, and hopefully it will be adapted as an OGC community standard very soon, and this is also very exciting for us. Scene layer package, a little bit description about scene layer package. Scene layer package could be this huge, gigantic file system format that allows you to pack the complete node tree structure and associated resources with it. And the archive actually also supports direct access of individual nodes and resources. And this is key for us, that you should be able to actually access the contents and the resource of a scene layer package directly within an application.
How big can they be, Tam?
So question is a trick question, actually. How big can it be? So one thing that we've done with a scene layer package, specifically with a point cloud scene layer package, is create this internal hash table or index that allows you to traverse this archive very fast. The archive is zip64, so there isn't any physical limitation really within it. But the only constraint that could come out of it is trying to access the index, the file index, to traverse a large data set. So what we have in store with point cloud layers, we want to put it across all layer types, that having this internal hash table that allows you to navigate or read through the file very efficiently is going to help it. So in that instance, I don't think there's any upper cap that we can say. So I3S, we envision I3S to serve as a common tool to package and disseminate a variety of GIS content. As Chris mentioned, it is released under the Creative Commons license, very liberal license, and is available on GitHub. And this is what these guys used to actually create the content. Occasional email from them here and there but other than that, they mostly were able to rely on that.
Yeah, their first layer was only 6 days after we told them about the GitHub link.
Yeah.
So it was really record time.
That's very encouraging for us, actually, to see that. So what are the tenets of I3S really? Web friendliness, mobile friendliness. We said that extensible. It needs to support different types of content within the system. The system also has to be declarative, in that the implicit knowledge required to understand or navigate the layer should be as minimal as possible. And efficiency and scalability are also key to it. It is scalable in that you can visualize, geographically large amounts of data sets, as well as very dense and high resolution data sets that you usually see with point cloud coverage. Protection is built in with the system. In fact, when you publish your content to ArcGIS Online or ArcGIS Portal, you can enable named user access or security on it, so that users that actually dearly want security to be enabled on this layer could also effectively do that. And as I said, specification is open and publicly accessible to anyone. So what are the different layer types and profiles that are found within the Index 3D Scene Layer specification? Scene layer types, so these two concepts of scene layer types and profiles are pervasive around the spec. Scene layer type has a strong affinity or relationship to the data type, to the geometry type of the data. There are 4 layer types that are fully specified and documented within the I3S specification. 3D objects, points, integrated mesh, which we have seen plenty of, and point clouds also are the 4 ones. Profile relates to how different sets of layers relate to each other. For example, both 3D objects and integrated mesh belong to mesh pyramids profile because they have the same bounding volume hierarchy, the same decimation rules and traversal rules that a client application could apply. So if you support one, you could easily support the other one. So these two concepts, layer types and profiles, are pervasive and found within the specification. So let's delve into the different layer types. 3D objects, 3D object layer types are your classic building shells, building exteriors that are typically sourced from GIS data, as well as 3D models that are imported from various formats. And these are your OBJ, Collada, SketchUp, and whatnot formats that usually 3D content generators use to generate. So 3D objects is the primal example of a layer type that represents, typically used to represent building exteriors and geotypical objects. The next type, integrated mesh. Integrated meshes are mesh surface representing, as my colleague Dragon calls them, the skin of the earth type of content, including vegetation, buildings, and roads, and cars, and people, really. It's everything that you can capture. This type of data sets are typically derived from satellite imagery, I guess in your case, aerial or drone imagery, as we mentioned in like a drone to map kind of case, via many processes, photogrammetric processes of dense matching and whatnot, or can also be directly calculated from sensor sources. Third type of layer type is points. Points are your canonical examples of POI of schools, hospitals, and trees, typically sourced from feature locations, but could also be combined with instanced 3D models that are generated either by hand or some automatic process. So a combination of a point feature class with a style or a symbology is actually a very rich and powerful way of symbolizing your scene, and we see typically customers do that quite often. So points are also supported layer type within the I3S specification. Lastly, the one that we have added, version 1.5, is direct support for point clouds. Point clouds, typically sourced from LiDAR data sources or sensor collected, are very pervasive, and they could be used to augment your existing GIS content, or used for asset verification, or many other applications. So those are the 4 types of layers that are fully documented, specified, and are supported within the I3S specification or standard. Okay, so let's talk a little bit about the data organization and structure within the I3S system. I3S organizes information using this hierarchical node-based spatial indexing structure, where each node's payload may contain features with associated geometry, texture, or attribute. Looking into one of these nodes, for example, the physical organization of this information within the node is as follows. Typically, there's central to it, central to the I3S structure is this node index document. The node index document is a lightweight JSON resource that describes the topology of the tree within the node and includes references to other sub-resources. So within using this node index document, the client application can actually navigate and traverse the tree with this topology very efficiently. So a node index document contains a few other resources or sub-resources. First one is the shared resource. The shared resource is a descriptor document for material and texture resources. So this is where material descriptors and texture descriptors are within the node index document. Second up is the feature data document. The feature data document is yet another sub-resource. It's again a by reference sub-resource. It's a JSON text resource that contains identifiers of the features within our node. So for a layer type like integrated mesh or 3D objects, really is the mesh segmentation information is stored in this feature data document that you could use to know the association of the mesh that you have and the features that it represents and from where it is sourced from. And then lastly, the binary resources. There's a geometry data, that's a binary resource, attribute data, and texture data. These are all sub-resources of an I3S node that describe geometry, attribute, and textures. Okay, next slide. Oh, I went forward. All right. So now let's talk a little bit about LOD models and the selection matrices available. Selection metrics available within I3S. I3S promotes this concept of discrete levels of details with multiple discrete representation of features and nodes, where a more detailed representation of a node and its features fully replaces a coarser representation at a lower level of detail. Such replacement strategy is applied across all features or elements that are covered by the node. So the content that you see within a particular node at a given level could completely be replaced by content that is ancestral node or as is children node, if any. Another concept within the I3S is this selection, availability of many selection metrics that allow you to actually select nodes based on different parameters. One that we use typically was 3D objects and integrated mesh layer types is this maximum screen size selection metrics that the node or the bounding volume, minimum bounding volume of the node may occupy on the screen before it is replaced with data from a more detailed node. So a combination of level of detail and selection criteria or the selection criteria would allow you to actually efficiently select and prioritize the content that you would want to display within a given application. We call this model of discrete LOD rendering within I3S as node switching. Let's talk a little bit about the consumption of content within I3S. So as we've seen, I3S content could be consumed in two ways. It could be consumed as a service via the REST API or locally as a file system. That's the one that Isaac has been showing us that hundreds and hundreds of gigabytes of data could efficiently be consumed because the SLPK itself kind of retains the complete node structure and associated resource within the package. So I3S nodes and their payloads, when they are resident on the server and are returned to the client via RESTful API, that's what we call it as a service. And all the associated nodes, all the nodes and their associated resources are also fetchable or addressable via web address. So each resource within an I3S content has its own web address or a REST API that you would be able to actually request the content. Similarly with the SLPK, the SLPK itself also mirrors similarly what the REST API of a scene service does. And in a follow-up diagrams, I'll be able to show what it looks like within the file structure itself. I3S is also very flexible. We do not try to impose, or we try not to impose requirements as much as possible as long as it's not needed. So there is a few flexibility within the system. Examples of flexibility include bounding volume specification allows you for having a minimum bounding sphere or oriented bounding box. And different layer types could implement different bounding volume strategy. We try to make it homogeneous across the system, but the actual specification is permissive of different bounding volumes. Another one is node structure, how the node structures are stored. Node structures could typically be stored expanded as they are in the case of 3D objects and integrated mesh, or they could be paged or fixed size, where we would be requesting not each individual node, but actually a page of nodes that package or that packs many nodes together. So such flexibility allows us to actually direct optimization to different layer types and be able to use it within different systems. Continuing on the flexibility of the system, nodes could be embedded. So, for example, the point layer type embeds the geometry within the feature data document itself. So this is an embedded geometry within a feature data, or it could be by reference, a binary. So all the information or the positional information for 3D object and integrated mesh layer types are all by reference, and they are all stored as binary. And the same for attribute content. It could be either embedded, or it could be a binary resource that could be fetched directly from the node itself as a sub resource. So such kind of differences and flexibility allows you to actually use the right tool for the right purpose. If you're creating very minimalistic data with a point feature, you might not need to be forced to go one route. And that's the whole idea about having a specification that allows you to use different features. Another area of flexibility, again, is the LOD selection metrics, metric types. Maximum screen threshold, as we said, is used by 3D objects, integrated mesh, and other layer types, points and point cloud actually allow or effectively use different LOD selection criteria. All right, we're running a little bit late on time, so I'll try to hurry up here. So key to scalability within I3S is indexing and level of detail management. The I3S specification itself does not impose any particular schema. You can use any type of data partitioning or schema as you see fit with your data type. Really, the whole idea is that you should adapt the data type to the type of schema that you would like to use. Quad trees are particularly good to tile regularly graded data, whereas sparse oak trees could be efficient to store and represent dense data such as point clouds. So the I3S specification itself does not impose one or the other as far as client consumption is concerned. But one thing to note here is that as much as possible, as much as humanly possible, it's always good to balance data across nodes so that we strive to achieve this near constant load of data within each node. I could go through the steps that we do to actually create I3S content within the Esri suite of software, but as we are running out. One thing that I would like to mention here is that I3S permits and actually effectively uses having this alternate representation in the interior nodes of a tree. So as you can see here, the leaf nodes could contain the highest resolution of the data, but the interior nodes, which are suitable to be visualized at different zoom levels, have alternate representation. And typically, with the data that we generate with the 3D object layer types, these are alternate representation of the input feature. So this is really a great way of creating multi-LOD structure out of input data that typically does not have multi-LOD associated with it. And we see this very typical with data that is provided either even as city JML or whatnot. There isn't a level of detail associated with it. Content like integrated mesh already comes with it, and there's nothing to do there. But typical GIS data input, they don't have that. And to supplement that, at least the cookers within the ArcGIS framework allow you to build this multi-LOD structure and be able to consume it. And the specification fully supports that. Same with level of detail. We routinely aggregate and decimate features to create different levels of detail within the I3S structure itself, so that while keeping the sanctity of the feature, that feature A is always recognizable as feature A throughout the tree, but it could be also coalesced or aggregated into a bigger node if it is too small. Same goes for very large data sets, that they could be split. Well, not per feature, but the whole idea is to be able to balance a node so that a node is always have this constant volume as much as possible. So the whole process is this capacity-driven texture and geometry reduction to create lower level nodes or lower level of detail. Quick overview of scene layer package. Scene layer package consists of this archive, zip64 archive that is never, that should not be a compression applied to it, because all the content within the archive itself, all the binary content within the archive itself is already zip compressed, gzip compressed. So the whole idea of this is that why Isaac was able to drag 150 gigabytes of archive is because the archive itself is not compressed. The content within the archive are compressed. So, for example, the node index document, the geometry, the texture, the compressed texture data, they are all compressed so that the size on disk is not humongous. But by not compressing the archive itself at the root level of the archive, we're able to actually directly access each individual resource. And this has been very useful and very powerful. And we're going to try to increment its utility by adding additional hash index within the archive itself, so that you can access it even faster. Here more about the scene layer package, how the layers are organized. As I said, each resource or each folder within the scene layer package kind of maps with the REST API of a scene service. Attributes, features, geometries, shared, and texture also map with it.
Just a quick comment that this stuff is simple enough for a PM like me to figure out.
Yeah.
So
very much. I'm happy.
I've ended up being the de facto QA on a lot of the scene layers, and like the first thing I do is crack open the file in gzip or 7-zip.
Yeah, 7-zip.
And I look at the compression. And right away, one thing that people break is they'll try to add compression into the files, and that they're designed not to have that compression.
Yeah.
So it's really been easy enough for me to open up these files, triage issues, get right back to Isaac or Bentley or Pix4D or the City Engine team who now makes I3S and broke some things at one point. Yeah. So I mean, it's really easy enough for anybody in this room to take a look at and start figuring out.
Yeah. No, this is great because basically what I was going to wrap up with let me bring it up in here. Oh, okay, well, it shows here. So here are some REST resources that are handy to keep within the ArcGIS enterprise system. What I use usually typically to find out my content, my services, even to submit some jobs, and also be able to discover the web scene and scene layer items and web scenes that I have within the ArcGIS enterprise. Similarly, you can also do the same with ArcGIS Online. As we are running a little bit short, it's not allowing me to go. I don't know what happened, but oh, here it is. Let me wrap up here with quick comments to follow. Here is a little bit about the geometry buffer type. Now, as I said from the beginning, that the I3S system is very declarative. So everything and anything that you want to know about the format of the layer is described within the layer itself. So the 3D scene layer JSON resource actually describes the content of the binary format. How many, what it contains. Does it have normals? Does it have regions? Does it have colors? All that information is described within the layer itself. So anybody that wants to look at actually I3S could look at one of these SLPK samples and be able to navigate. And I think that's what you guys did, actually look at actual content. So we're running about 4:55 right now. So maybe at this point, should we open it up for a question?
Yeah, Darren, do you mind getting the, thanks for hitting the lights earlier too. I think that was a much better experience for everybody. Questions, folks? What do you guys think? Is this new, completely new? Go ahead.
So can you just talk a little bit about how to I'm interested in taking a LiDAR file and generating an I3S format from that.
Sure.
What are the tools you use to do that?
Sure, I'll repeat the question for the tape. So the question is, how can you generate an I3S point cloud scene layer from a LiDAR file? So Tam can take that.
So in ArcGIS Pro, actually, there is a tool, the Create Scene Layer Package tool. I just pulled it up right here. That allows you to actually input in LiDAR data sets and be able to generate a point cloud. So the most typical way of generating a point cloud scene layer is through the Create Scene Layer package. In the future, we'd also add ability to directly publish to ArcGIS portal or ArcGIS online LiDAR or point cloud scene layers. Currently is by creating a scene layer package within ArcGIS Pro. That's the one way to do it.
Yeah, and Isaac, do you want to talk any about how you guys actually generate it? Because you don't use any Esri technology.
No, we don't. So
Is your mic off?
Yeah.
Can you hear me now?
Yeah.
So in our scenario is actually a little bit more straightforward because our data starts as a multi-LOD tree structure to begin with. So we build out as part of our original production process. I think we have too many people too close here. I'll come up here.
Yeah.
So for us, as part of our standard production process, we actually build out the tree structure in our kind of intermediate format, which is a format that we use internal to our own company. So for us, we're able to just take the exact same tree structure that we've already created and pull the geometry straight out of the format that we have and the textures straight out. So we recompress the textures. Now that we've learned that DXT compression is actually important, despite the fact that it makes it really big.
Yeah.
So we recompress the textures, and then we built a tool internal to our production process to spit out the JSON metadata per node, and then actually package it all together. So from a development standpoint, it was not a very heavy lift on our side to add that as a kind of standard export for our own process.
Yeah, but you guys had the pipeline that already generated the multi-LOD data. So.
Yep.
How about any other questions? Let's start one in the back first.
Kind of related to his question, is there anything that needs to be done to that LAS data set or anything prior to, like, I have to do blur compression usually?
I can just answer you that one. So the answer is no. In one case recently, I was in a hurry and I got some data in ellipsoidal projection, and I just manually adjusted it to the right elevation, which is not the right way to do things. So you might, if you need to convert possibly to the right projection or coordinate system, then you may have to do some standard operation like that. But it is literally bring it into a scene in Pro, right-click on it, share as scene layer, as web layer, and it starts to process, and it's fast too. The DC data is a couple of gigs at least, and it cooks a scene layer in, I don't know, 45 seconds a minute, something like that. It's fast. So, there's another question. Yep.
I missed this earlier, but the Vricon imaging, is that available in ArcGIS online?
So go ahead, Isaac.
So there are a couple of very small samples that are up on kind of the broad public onlines right now. We actually just had this conversation earlier this week. We're gonna put a few more kind of relevant, interesting sample components up into ArcGIS Online, but it's not a standard part of like Living Atlas or something like that. So if you want more information about how to get our data,
If you see Jack in the hallway and you say, "Hey, I heard
Exactly.
Ricon's going to have this globe of the Earth in 2 years. Can you please make it available to us?"
that's right.
Other questions? Yes, sir.
So if I have a scene layer package and I go to publish that now with Pro to my own ArcGIS Enterprise instance, is there an existing workflow to make sure that persists to S3? Or is that all kind of manual?
That it persists to S3.
In terms of the integration, right? Like if I've got tips, I want to make sure those are registered. There's existing Python tool sets, right, to do that. Is there a similar transport for this?
So if I understand your question correctly, so you want to take an SLPK layer, an SLPK package, and publish it as a service on ArcGIS Online or Portal, and you want to be able to associate it with what exactly? I wasn't clear.
Just if I'm taking that 120 gigs, that it's, I'm ensuring it's being stored.
Oh yeah, okay. So I see. Okay. So when you take 120 gigabyte of SLPK and publish it to ArcGIS Portal, what happens is we actually pour that content into the managed data store. So in the case of Portal, it goes into this into the data store database that we have. That's what it goes. And in case of ArcGIS Online, it could go into either Azure blob storage or S3 blob storage, S3 storage. So the content is stored not as 150 gigabyte of SLPK, but is stored in S3 or Microsoft Azure Blob Storage and Online, or into CouchDB in the case of Portal when you actually publish it.
My portal's configured.
Yeah, as long as your portal is configured to use that, you should be able to access the point, be able to identify so when you publish, so there is one distinction though. When you publish directly from ArcGIS Pro, a feature layer, for example, the association between the feature layer as a feature service and the scene service layer is maintained, so that when you do identify or query, you would be able to hit the feature service as well. And the web scene application and Pro does that. What we have done in the last release was actually be able to include the attribute information also with the scene package, so that even when you publish just the scene package layer, you should be able to do the same thing, identify and find things that you would want. So we're trying to keep as much as possible with the scene layer package information that you would need for identifying or discovering content.
To kind of follow up on that workflow, is there the concept of being able to aggregate these different scenes together when building out a global layer, or is it kind of tile by tile there? Is that TBD?
You can. So the one web scene, it really depends. You could actually generate a data set that's a single layer that's huge. We haven't actually experimented with anything that's global coverage yet, but in fact, the largest ones that we've seen are the 10,000 square kilometer geocells. That's just their pipeline. It's not any limitation. The other thing you can do is just like I did in the one web scene is you just link together. You can group together many layers in a web scene. So
and that was actually what I was
I'll make one correction, one caveat. The lighter weight clients don't have the best tech for managing caching across many layers. So if you're in a situation, which a lot of people in the BIM world, building information modeling world, are trying to do this, where they're separating out all their assets into multiple scene layers that are all coincident in space, and then they're trying to view all the pipes and plumbing and walls and everything at the same time. In that case, the web scene viewer especially will slow down somewhat, and I suspect Earth also would run into issues. So in that case, it's actually better to publish that data as a single scene layer and then use other tools, API, to filter it and manage it. So there's, to some extent, this stuff is still evolving, and but there are some nuances like that where you can do either one, but it also depends upon what the actual user experience is around the data itself. So one kind of add-on to your comment that I get quite a bit is that a data vendor wants to push data up to their own S3 instance and then hook it up by reference to items in online. We have not yet built that out, but we're hearing that quite frequently from some of the data vendors. Like I'm sure you guys would like to be able to do that kind of thing. So that's something that we're hearing about.
Yeah. Just
Any
on
other-
that point, though,
Yeah.
the I3S specification actually right now allows to do that, and we did experiment this. So
Cool.
I just pulled up the specification right now, and if you go to the bottom of the spec, this key value stores is exactly that.
Awesome.
If you want to store your content in your own key value store, S3 or Azure, and don't want to use Esri's ArcGIS online or portal infrastructure, you can do that. There is no limitation in actually in the specification itself.
Before you all go, I just want to point out Dragon over there as well. If you see Dragon and you have questions, he's the senior guy on our whole team. He's driven a lot of this from scratch, and he can definitely tell you some of the details about how everything works as well. I'm really lucky to work with these guys, so it's really been a pleasure to work on this and have great partners like Isaac and Fricon for sure. Yep. So is there one last question that anybody wants answered? So we're already over time, and I just want to be sensitive to your time. All right. Well, thank you guys very much.
Thank you.
We appreciate your time.